For decades, enterprise computing was entirely bound by physical constraints. Scaling meant ordering custom hardware and running miles of copper cabling by hand. Modern computing relies on the decoupling of physical computing hardware from the execution environment. This is abstraction. By introducing an intermediate layer of software, engineers can translate rigid silicon and steel into pure logic, manipulating global infrastructure entirely through code. The cloud functions as a strictly defined architectural framework that makes physical hardware agnostic to the applications running above it. To build or secure systems in environments like AWS or Azure, you must first understand the abstraction models that govern them. The baseline for this architecture was codified by the National Institute of Standards and Technology. Their publication, SP 800-145, serves as the defining text for what actually qualifies as cloud computing. They define it as a model enabling ubiquitous, convenient, on-demand NetApp access to a shared pool of configurable computing resources. This definition is supported by a tripartite structure: 5 characteristics, 3 service models, and 4 deployment models. The service models dictate what stack layers the provider manages versus the client. Finally, the deployment models define the logical boundaries of who accesses the underlying hardware. Whether you are running a private OpenStack cluster or a global AWS deployment, the underlying infrastructure must perfectly map to this framework. The first requirement is on-demand self-service. An engineer must be able to provision compute power automatically without requiring manual intervention from the service provider. Second is broad network access. These resources are distributed and accessible over the network through standard mechanisms, decoupling the user's location from the hardware. Third is resource pooling. The provider's physical hardware is consolidated to serve multiple consumers simultaneously, dynamically assigning resources according to demand. This creates the environment known as multi-tenancy. Fourth is rapid elasticity. The system can automatically scale outward to absorb high traffic loads and elastically scale inward to release unused capacity. Finally, measured service. Every millisecond of CPU usage, byte of storage, and packet of bandwidth is continuously metered, allowing precise billing based entirely on consumption. If an IT environment fails to meet all 5 of these mandates simultaneously, it operates as traditional hosting, not true cloud architecture. This specific diagram illustrates the core SPI service model stack, starting immediately with the foundation, Infrastructure as a Service, or IaaS. In IaaS, the provider supplies the virtualized hardware. The engineer retains administrative control over the operating system and the applications running on it. Platform as a Service abstracts away the underlying operating system. Engineers provide application code, and the cloud provider manages the execution environment. At the top is Software as a Service. The entire stack is managed by the provider and delivered directly to the end user. These service layers exist within 4 physical deployment models: public, private, hybrid, and community clouds, which dictate exactly who resides within the resource pool. Selecting a target on this matrix determines the precise ratio between system control and operational overhead. But what specific software mechanism makes abstraction and resource pooling physically possible on the actual bare metal silicon hardware? The engine driving cloud computing is the hypervisor, also known as a virtual machine monitor. In enterprise environments, this relies on a Type 1 bare metal architecture. The hypervisor software sits directly on the physical hardware, intercepting all system commands. It partitions the physical CPU and RAM into isolated, software-defined chunks known as virtual machines. In the enterprise space, this operational standard is largely defined by the VMware ecosystem. VMware's ESXi is a specific, widely deployed implementation of a Type 1 bare metal hypervisor. To manage a data center, vCenter is introduced as the orchestration layer, controlling dozens of hosts. This orchestration enables vMotion, which allows administrators to migrate running virtual machines across servers seamlessly, without downtime. It also provides high availability. If physical hardware degrades, the system executes an automated failover, instantly booting the affected virtual machines on healthy hosts. The hypervisor is the essential mechanical tool that directly pulls theoretical NIST characteristics out of abstraction and into physical reality. Transitioning from local enterprise clusters to massive public infrastructure brings us to Amazon Web Services. Because AWS operates on a scale of extreme multi-tenancy, It requires rigorous logical network segmentation. This segmentation is established by the Virtual Private Cloud, or VPC. It provides an isolated network environment where engineers deploy their resources securely. Within that boundary, security groups enforce access at the micro level. They act as virtual firewalls attached directly to individual compute instances. Mastering VPC boundaries and security group logic is the prerequisite for preventing breaches in multi-tenant environments. Operating this architecture requires moving beyond graphical consoles and managing infrastructure through the command line interface. For example, spinning up compute capacity is executed with a command like AWS EC2 run instances. This command acts as an API call, directly instructing the AWS hypervisor to allocate physical hardware from a data center rack. The command specifically invokes an Amazon Machine Image, or AMI. This is the exact software template applied to that carved-out hardware slice to load the operating system. Executing this command is the direct application of NIST's mandate for on-demand self-service. In the upcoming practical lab session, you will utilize these CLI commands to build your own virtual private clouds. Successfully managing these systems requires seeing past the graphical web console, understanding the invisible hypervisor abstractions, and orchestrating them